Okay. The other questions are, that should be, other questions are, that is Schrödinger wave equation for particle in one dimensional box. That is also not found in many books, okay? And also some beautiful concept of Raman spectra and the rest of the gas equations. Now we come Schrödinger wave equation for a particle in one dimensional box, that is 1D, and its energy. The simplest problem related to that particle in a microscopic system, that should be say electron in the atom, involves this type of box, okay? That is wave mechanical treatment of a particle in a one-dimensional particle box, and the two walls of the boxes are 1 and 2. Okay. Inside of the box we get V equal to 0. Okay. V equal to 0. That should be potential energy, I think, potential energy, and that is out of the box, that should be V equal to infinity and V equal to infinity. Okay. And psi also 0 here and here. Psi equal to 0 and V equal to infinity. In box, potential energy V equal to 0. Okay. A is the length. As we know, x equal to 0 to x equal to a, that means the whole length of the box, that should be a. Okay, that should be a. Now with derivation we use, that is the Schrödinger wave equation with respect to space, that is must be d square psi by dx square, that is del square psi by del x square plus del a square psi by del y square plus del square psi by del z square plus 8 pi square m by h square e minus b into psi equal to 0. Here we can say that is in 3-dimensional, the psi function can be derived by this way, that is del square psi by del x square plus del square psi by del y square and del square psi by del z square. That should be z, okay? That should be z. Okay. And 8 pi square m is the mass of the particle, that should be considered, and h is the Planck's constant, E is the total energy, and V is the potential energy, and psi equal to 0. Okay. Okay. For a particle moving on the one x direction, we only consider for x coordinate only, that is del square psi by del x square plus 8 pi square m by h square e by e minus v into psi equal to 0. Okay. For within the box, as we know, in this side, that is v equal to 0, that is potential energy equal to 0. So that indicate v equal to 0. So we can put in this equation v equal to 0. So by this we can get, that is del square psi by del x square plus 8 pi square m by h square e psi equal to 0. We can this term to that is this side. By this we can get the del square psi by del x square equal to minus 8 pi square m capital E by h square into psi. Del square psi by del x square equal to minus 8 pi square m capital E by h square into psi. Okay. Solution of equation 1, and since pi m and capital E and h are constant, equation can be written by this way. That should be del square psi by del x square equal to minus k square hash psi. That should be k square equal to value, we get 8 pi square m capital E by h square. That is this value by this value equal to, we get k. We get k. Okay. By this way we can use this and we can derive this, that is d square, that is del square psi by del x square equal to minus k square psi, where k square equal to 8 pi square m capital E by h square. Okay. Okay. So what we get, that is first one, Schrödinger wave equation, del square psi by del x square, del square psi by del y square, and del square psi, then z square 8 pi square m by h square e minus b into psi equal to 0. Now as x direction we consider, that is this reduced part is del square psi by del x square plus 8 pi square m by h square e minus b into psi equal to 0. By this way, we can get this also as b equal to 0. Putting it, we can get del square psi by del x square equal to minus 8 pi square m capital E by j square into psi. Okay, now consider this whole term as a k. So, k square equal to 8 pi square m capital E by h square, that should be del square psi by del x square. Now we get del square psi by del x square, that is minus k square psi. Okay. Now psi equal to c1 e to the power ikx, c2 e to the power minus ikx. We can represent this. Okay, general solution. An equivalent and more convenient form of this equation, with many of the cases we derive, is psi equal to a sin kx plus b cos kx. Psi a sin kx plus b cos kx. Equation represent all the solution of equation which are mathematically satisfactory. However, mathematically can be satisfactory, and this solution do not necessarily satisfy our boundary condition. There is no need to consider the boundary condition. So we now must examine equation in view of the requirement also. That's why we have to examine this. Okay. So differentiating the equation, that is with respect to del square psi by del x square. As we know, psi equal to a sin kx plus b cos kx. So we differentiate with respect to k, that is must be, that is x, that is a sin kx plus b cos kx. We differentiated it and we get ultimately minus k square a sin kx plus b cos k. Differentiating it, apply boundary condition, we get x equal to 0, psi equal to 0. So that is, as we know, sin 0 is a 0, cos 0 also 1. So we get what? That is minus k square 0 plus b, that is ultimately 0. That is, we get b equal to 0. We get b equal to 0. Apply this, we get psi equal to a sin kx. Psi equal to a sin kx. Okay, a sin kx. Okay, that is double differentiation. Okay. So ultimately we get what? That is psi equal to a sin kx. And we also get a sin n pi x by lambda. Okay, n pi x by a, sorry. N pi x by a. Okay. Now we consider Raman effect. Suppose, okay, this, there must be h nu come, okay, that should be emitted. This emitted frequency, that should be h nu, okay. That should be incident frequency, h nu. Go, that should be h nu dash, that is must be, which can be emitted frequency. If their energy are same, that is called Rayleigh line. Rayleigh line or Rayleigh scattering. That is, incident energy or incident frequency equal to emitted frequency or emitted energy. That is called elastic collision. No transfer of energy can be there. Okay. But for Raman scattering, that is, viewpoint are defined. There should be h nu not equal to h nu dash. How we consider? This. Okay. There must be, suppose in Stokes line like that, h nu dash, Stokes line, Raman scattering, that is anti-Stokes line. Okay. That should be not equal. So in one case, h nu equal to h nu dash plus e. I think there should be anti-Stokes, I think. And h nu equal to h nu dash minus e. Okay. That should be Stokes line. But I am not sure now that, but we have to check. But that is should be there. That is h nu equal to h nu dash plus e. That should be anti-Stokes line, and means that H nu is much greater, and H nu equal to H nu dash minus E, that should be Rayleigh line. Okay, so that should be Stokes line. Okay, now we consider there should be Rayleigh scattering that should be highest intensed. Okay, as we know that is H nu equal to H nu dash. Okay, then other Stokes lines and anti-Stokes line. Anti-Stokes lines are lower intensity because there should be transition from excited state to ground state can be considered. So as we know, that is population of molecules that should be more in ground state rather than excited state. Obviously, always they should be stay in their stable life, right? Similarly, molecules also like their stablest form. So always they should be love to stay in ground state energy, and they are in ground state population that should be more. So more transition can be feasible, more intense lines are there. So Stokes lines are more intense than anti-Stokes line. Okay. Okay. Now we consider that is nu A is the frequency of scatter radiation, nu I is the frequency of incident radiation. Okay, there is no problem. Okay, now we get, there should be, by this way Raman spectra, we get this type of peaks. Okay, this middle portion line, that is must be Rayleigh line, that is del J equal to 0. J is the rotational constant, that should be del J equal to 0. Okay, and if goes this side, that is must be J plus 2 to J, there should be anti-Stokes line. If you go this side, that is J plus 2, then J to J plus 2, we consider Stokes line. Okay. If we go J plus 2 to J, we get anti-Stokes line. If we go, that is J to J plus 2, we get Stokes line. Okay. Okay. Middle portion, Rayleigh line. Okay. Okay, now consider their spacing, the Rayleigh line and the fast Stokes line and anti-Stokes line. In both of the cases, Rayleigh line and their fast anti-Stokes line difference, that should be 6p. Okay. And Rayleigh line and that is fast anti this should be fast anti-Stokes line and this should be Stokes line. Fast Stokes line and Rayleigh line, the difference should be 6p also. So what we understand, that is Rayleigh line to fast Stokes lines as well as fast anti-Stokes line, the spacing is, or the difference is 6b. B is the rotational constant. B is the rotational constant. Okay. Okay. Next we consider, that is in between of two anti-Stokes line, the difference is 4b. Okay. And between two Stokes line, the difference is 4b. That is also same spacing. Okay. Okay. Last one, some gas equation, that is Van der Waals equation. Van der Waals equation, that is P square. If there must be Van der Waals equation, that should be applicable for real gases. As we know, for ideal gas equal to PV equal to nRT, right? But actually ideal gas shall not exist. Okay, so we have to derive real gas. Okay, for real gas we derive Van der Waals equation. That should be P equal P plus N square A by V square P minus NB equal to nRT. When for 1 mole of gas, that is N equal to 1. That is P plus P plus A by V square, V minus B equal to RT. Okay. P plus A by V square, V minus B, that should be equal to RT. Where V is what? V is the excluded volume or co-volume. That is 4 into actual volume of gas molecule. 4 into actual volume of gas molecule. And A is nothing but magnitude of attractive forces between gas molecules. There should be magnitude of attractive forces between gas molecules. The greater the value of A, the greater strength of van der Waals forces. The van der Waals forces, that should be much greater. When A increases, the strength of the van der Waals forces, that should be increases, is with which a gas can be liquefied. So by this way we can derive that P equal to N square A by V square, or equal to PV, or we can derive PV square, this should be one equation, P equal to N square A by V square, and that should be equal to A. That is, there must be mistaken, huh? That should be A equal to PV square by N square. Okay, N square, PV square by N square. That is, P is the ATM. Okay, P is the ATM. L means liter square and N is the mole. Mole square means mole to the power minus 2. That is ATM liter square mole to the power minus 2. That is P. For pressure we get ATM. For V we get liter square, and for N square we get mole square divided by mole square. That should be ultimately we get mole to the power minus 2. Okay. Now we consider V equal to NB. Okay. V equal to NB. Ultimately we get B equal to, that is must be one equation. Okay. B equal to V by N. Okay. V by N. That is must be for V we get liter, and for N we get mole inverse. For V we get liter, for N we get mole inverse. The van der Waals equation deviates at very high temperature and low temperature. At very high pressure and low temperature. Okay. So liquefaction of gases and critical points, that should be critical temperature Tc. Tc means nothing but Tc equal to 8A by 27 Rb. B and A, that should be same. B is the excluded volume or co-volume, and A is the magnitude of attractive forces between gas molecules. Okay. So Tc, that is a critical temperature equal to 8A by 27 Rb. At 1 atm pressure, boiling point is known as normal boiling point when air pressure is 1 atm. Okay. So, okay. Okay. Ultimately critical pressure PC, that is equal to A by 27 B square. A by 27 B square. That is 1 bar pressure boiling point is known as standard boiling point. When 1 bar pressure, that should be there. That is called standard boiling point. Okay. Critical volume, that is also VC. That is VC equal to 3B. VC equal to 3B. Okay. Now boil temperature, that should be TB equal to A by PR. They are basically they are formulas. That is boil temperature equal to TB equal to A by PR. Okay. Now surface tension. Surface tension nothing but that is how they attach with surface, like this type of tendency. Okay. That is SI unit Newton meter inverse. Newton meter inverse means why? Because surface tension equal to force by length. Due to force we get Newton, and due to length we get meter. So by this way in SI unit we get Newton meter inverse. Okay. Dimension, that is kg second to the power minus 2. Okay. And that is eta. Eta is the viscosity. So that should be, now we consider viscosity. Viscosity means how, that is their flow of, if any liquid having higher viscosity, their flowness that should be decreased. If they are low viscous, their flowness that should be more. If we consider Hg, that is mercury and water, mercury is more viscous, so their flowness is very much less than water, but water is less viscous, so it can be flow easily. Okay. F equal to force equal to eta A dV, that is difference in volume by dz. F is nothing but force required to maintain the flow of layers. In between of layers there flow. There must be not one liquid flow. In a liquid there must be so many layers are present. Okay, and all of the layer they are flow condition. Okay, their forces are called, there are forces that should be required to maintain their flow, that is called F. Okay, A is the area of contact. Okay, and dB by dz is nothing but that is a velocity gradient, the change in velocity with distance. With respect to distance, the change in velocity, that is called velocity gradient. And n is the proportionality constant. As we know, when we derive some proportionality symbol, after omitted the proportionality symbol, we get some proportionality constant. Here also eta also a proportionality constant in this equation, and we call this is a coefficient of viscosity. Okay, coefficient of viscosity. And the value of eta, that is CGS unit poise and SI unit Newton meter to the power minus 2. CGS unit poise and SI unit Newton meter to the power minus 2. Okay.